Imagine a world where the most powerful language models were bottlenecked by how quickly they could read a sentence, one word after another. That was the challenge before the transformer.
We've seen these models, like LSTMs or GRUs in previous cases. They process sequences well, but what exactly was the fundamental limitation of those recurrent or convolutional networks?
They're inherently sequential. Each step relies on the previous one. This made them slow for very long sequences and hard to parallelize, especially for training on huge data sets.
Most dominant models, particularly for tasks like translation, followed an encoder-decoder configuration. The encoder summarizes the input, and the decoder generates the output based on that summary.
Right, the encoder creates a thought vector, we've called it before, but then the decoder still had to process that sequentially, didn't it?
Precisely, and even the best-performing models tried to mitigate this with an important addition. They also connect the encoder and decoder through an attention mechanism.
So attention wasn't entirely new in 2017. It was an enhancement to existing models, helping them remember longer sequences.
Correct. But this paper proposed something radical, a new, simple network architecture, the transformer. We introduced its core mechanics in case TCM 183005.
Ah, yes, the initial architecture. So this is the paper where it all started?
Exactly. The big shift was that it was based solely on attention mechanisms, dispensing with recurrence and convolutions entirely. No more sequential processing as a bottleneck.
That sounds almost too simple. How can just attention do everything a complex recurrent network used to do?
It's a common initial thought, Maya, but the results were undeniable. The transformer showed superior in quality while being more parallelizable for training.
So faster training and better results? That's a powerful combination.
On a benchmark like WMT 2014 English to German translation task, it achieved 28.4 blue score, a significant improvement over prior state-of-the-art models.
That's a concrete metric of how much better it was at understanding and generating language. For context, BLU, Bilingual Evaluation Understudy, scores measure how closely a machine's translation matches a set of human references, typically ranging from 0 to 100. Achieving 28.4 BLU was a substantial leap for its time.
And the implications went beyond translation. The paper demonstrated that the transformer generalizes well to other tasks, like English constituency parsing.
This points to attention being a general-purpose computation, a concept we explored in case number TCM 213005, right?
Absolutely. But to fully grasp how a simple attention mechanism could achieve such feats, we need to build up an intuition for what attention truly is from its origins.
Think about human perception. When you look at an image, you don't process every pixel equally. You pay visual attention to different regions of an image.
Like focusing on a face in a crowd, and the background becomes blurry. We prioritize what's important. While it's like blurring, remember the model's importance is a calculated weight, not a human subjective experience.
Exactly. In deep learning, attention can be interpreted as a vector of importance weights. It tells the model which parts of the input are most relevant to the current task.
So instead of just blurring, the model assigns a numerical importance to each part.
Before attention, traditional seek-to-seek models struggled with long inputs because their fixed-length context vector design is incapability of remembering long sentences.
That thought vector we mentioned from the encoder, it had to compress everything, losing details for longer inputs, right?
Precisely. The paper describes the secret sauce invented by attention as creating shortcuts between the context vector and the entire source input. This was the key innovation.
So instead of one compressed summary, the decoder gets to look back at specific parts of the input as needed, like consulting notes.
That's a good analogy. Formally, this blog post defines the context vector for each output step as a sum of hidden states of the input sequence, weighted by alignment scores.
Weighted by alignment scores? Is that the importance weights you mentioned?
Yes, an alignment model assigns a score to each input-output pair. If you're translating dog, it might give a high score to the German word for dog and low scores to others.
It's like deciding which source words are most relevant for predicting the next target word.
Crucially, the weights of these shortcut connections are customizable for each output element. This means the model can dynamically decide what to focus on at every step.
So it's not a static summary, it's a dynamic, adaptive focus, just like our human attention shifts.
Yes, much like human attention, except that the model's focus is purely a mathematical function, assigning numerical weights, not a conscious process. This dynamic weighting means dependencies between source and target sequences are not restricted by the in-between distance anymore. Long-range connections are handled directly.
That solves the forgetting long sentences problem neatly.
The transformer scale dot product attention can be broken down into specific steps. First, for each input element, we transform it into three different vectors: a query, a key, and a value. The input to this attention mechanism consists of queries and keys of dimension dk and values of dimension dv. Think of the query as what I am looking for, key as what's available, and value as the actual information to retrieve.
So query, key, and value aren't arbitrary? They have distinct roles?
Exactly. To find how much each query attends to every key, we compute the dot product of the query with every key. This gives us raw alignment scores. Then we divide each by square root dk, where dk is the dimension of the keys. This scaling prevents the dot products from becoming too large, which helps stabilize gradients and avoids issues where the softmax function may have an extremely small gradient, hard for efficient learning.
And after scaling, it's normalized, right?
Yes, we apply a softmax function to obtain the weights on the values. This turns them into probabilities that sum to 1, indicating the relative importance of each key to the query. Finally, we multiply each value vector by its corresponding softmax probability and sum them up. This weighted sum of value vectors becomes the output for that query, representing a new, contextually enriched representation of the original input element, focusing on the most relevant parts.
So the full computation is query.key transpose, scaled, softmaxed, then multiplied by value and summed?
Precisely, that's the core calculation for a single attention head.
But the real leap for the transformer came from applying this attention mechanism not just between source and target, but within a single sequence itself. The key innovation in the transformer was self-attention, also known as intra-attention. It's attention applied to the relationships within one sequence.
So instead of relating an encoder's output to a decoder's input, it relates parts of the input to other parts of the same input?
Precisely. The definition here is clear.
relating different positions of the same input sequence in order to compute a representation of the same sequence.
That's like asking each word in a sentence, which other words in this same sentence are most important for understanding me?
Think of it this way. When processing the word bank, self-attention can look at other words like river or money in the sentence to understand its specific meaning.
It's building context for each word, but from its peers in the sentence, rather than a separate summary.
This idea of intra-attention had roots even before the transformer. The long short-term memory network paper used self-attention to do machine reading.
So the transformer didn't invent self-attention, but it showed it was powerful enough to be the sole mechanism for a model.
Yes, this table here shows different ways to calculate attention scores. For self-attention, the self-attention can adopt any score functions above.
So the specific dot product or additive formulas are just different ways to quantify the correlation between positions?
Yes, they're how we compute query key dot products. The scaled dot product attention in the transformer adds a scaling factor, 1 over the square root of n, to stabilize gradients, which is a subtle but important detail.
It seems like a lot of these smaller details are about making the training process robust, not just the concept itself.
Absolutely. This blog post also distinguishes between global/soft attention, which attends to the entire input, and local/hard attention, which focuses on a smaller patch.
And the transformer's self-attention, by looking at all other tokens, aligns more with the global/soft approach.
Exactly. This global dynamic mechanism is why we called the transformer's attention powerful general-purpose computation that adapts to any data that can be tokenized in case number TCM 213005.
While self-attention is incredibly powerful, it's important to acknowledge its limitations. A significant one is its quadratic computational cost. Calculating attention for every word with respect to every other word means the processing time and memory usage scale quadratically with the sequence length.
So, for extremely long texts, like an entire book, it becomes very expensive or even impractical to run memory-wise?
Exactly. This quadratic scaling can be a bottleneck for processing very long sequences. Another key point is that self-attention by itself doesn't inherently understand the order of words. Since the model contains no recurrence and no convolution, in order for the model to make use of the order of the sequence, we must inject some information about the relative or absolute position of the tokens in the sequence using positional encodings.
So it's not a silver bullet, but a powerful tool with specific strengths. And these trade-offs are important to understand?
Precisely. Knowing these assumptions and limits is crucial for applying these models effectively and understanding ongoing research to address them.
And that ability to build rich contextual representations for each word using only attention laid the groundwork for models like BERT.